Welcome back. In this video, we're going to talk about counting principles. So we've talked about counting a little bit. We've talked about sets and Venn diagrams, and those are some ways in which we can, those are some things that can help us count the number of elements in certain events. What we're going to be looking at today are some more advanced counting methods using a few different formulas. So let's start off with the multiplication principle. The multiplication principle says that if there are n ways to perform event A and m ways to perform event B, then there are n times m ways to perform events A and B. So we've actually already used this, we just didn't define it yet. When we rolled 2 dice, what we ended up with was a 6x6 table. And so there were 36 outcomes. And that's because when we roll the first die, if we call that event A, there are 6 possible outcomes, any one of the 6 numbers. And then when we roll the second die, there are 6 outcomes for that die. So we end up with 6 times 6, or 36 total outcomes. So that's the multiplication principle, and it's going to, we kind of use it by itself, but then there are a couple other things that we'll use, counting methods that we'll use that are applications of the multiplication principle. But let's look at a couple examples where we would use the multiplication principle. So the first one, how many 5-digit zip codes are possible? So Fayetteville, or the University of Arkansas at least, is in the zip code 72701. So from that, we can see with a zip code, it's 5 digits. We've got the numbers 0 through 9. We can repeat digits. Again, University of Arkansas, 72701. So there's 2 7s in that. So if we want to figure out how many 5-digit zip codes are possible, the way I like to do it is I like to draw a blank for each of these. So for each of the 5 digits. And then in each blank, I'm going to put the number of different options we have for each of these digits. So the first digit, it can be anything from 0 to 9. So that's 10 different digits. The second digit could again be any number between 0 and 9. So that's another 10. The third digit, another 10. And then the fourth digit, another 10, and the fifth digit, another 10. For each of the 5 digits, we have the numbers 0 through 9 to choose from. What one number is doesn't affect what any subsequent numbers are. So our multiplication principle, we defined it for 2 events, A and B, but we can extend it to any number of events. So how many 5-digit zip codes are possible? We can find by multiplying 10 times 10 times 10 times 10 times 10. Which is going to give us 100,000 zip codes. So there are 100,000 zip codes in the U.S. that are possible, assuming every one of those zip codes, every 5-digit combination is an allowed zip code. Let's look at a few other examples. First, how many 5-digit zip codes are possible if the first digit can't be a 0? So we again have 5 digits, so 1, 2, 3, 4, 5 different choices. Now we're told that the first digit can't be a 0, so we have to remove one of the choices. So there were 10 choices, now there are 9 choices for that first digit. Now it doesn't say anything about digits 2, 3, 4, or 5, so all of those could still be any numbers from 1 to 9, so that's 10 choices. So we have 10, and 10, and 10, and 10. So multiplication principle said we would multiply each of these together. So we have 9 times 10 times 10 times 10 times 10, and that's going to give us 90,000 different zip codes. Our last example with the multiplication principle is how many 5-digit zip codes are possible if the first digit can't be 0 and digits can't be repeated. All right, so 5 digits. First digit can't be a 0, so there are 9 choices. Now the second digit can't be whatever the first digit was because we can't repeat digits. So if we think about the first digit, the only thing we can't use is 0. We can't use that one. The second digit, we actually can use 0 because it says only the first digit can't be 0. So we add 0 back in. So we're back to 10, but we have to remove whatever digit we used first. So if we used a 7, we have to take out the 7. But that's the only digit we can't use out of the digits 0 through 9. So there's actually still 9 choices. So again, if the first digit was 7, we'd have 0 through 6, and then 8 and 9. So those would be the 9 digits that we could use. All right, the third digit just can't be the same thing as either of the first 2 digits. So we start at 10, and then we have to remove those 2, so that takes us to 8. Fourth digit, it can't be any of the first 3 digits. So we start with 10, we have to remove those 3, so that's 7. And then the next digit, as you can probably see the pattern, would be 6 because there would be 4 digits that we would not be able to use. All right, so multiplication principle would say that we would multiply these together to get our final answer of 27,216 zip codes that are possible if the first digit can't be a 0 and we can't repeat any digits. All right, now let's look at our first kind of application formula for the multiplication principle. And that is permutations. So permutations, that is the number of ways to select r different objects from a group of n objects where order matters. So now we're talking about selecting a group of things. So in a previous video, we looked at counting with cards, for example. So the number of ways to get a heart, for example. That would be if you drew 1 card from the deck. Now what we're doing is we're looking at selecting groups of things. And so selecting one thing is actually pretty easy. So the probability of selecting 1 heart from a deck, that's 13 out of 52. There's 13 hearts and 52 cards. When we start selecting more than 1 object, it gets significantly more complicated. So, anyway. So permutation is the number of ways to select r different objects from a group of n objects where order matters. All right, so let's look at this example. So in a race of 8 people, how many top 3 finishes are possible? So if you think about 8 people running a race, and let's as an example, let's say the person who gets first place, their first initial is G. And the person who gets second place, their first initial is S. And then the person in third place, their first initial is C. All right, so that's our order. So first place, G. Second place, S. Third place, C. So is that the same outcome as S, G, C? And the answer is no, that's not the same outcome, right? It's the same 3 people, but it is not the same outcome. So permutations are when we can have the same grouping, but they're in a different order. Now, when I say order matters, some people see that and think, okay, order must be important to someone. But that's not really the case. So in this problem, in a race, these people probably do care. The person who gets second place probably wishes they had gotten first place. So it matters to them. Now, that's not always going to be the case. Sometimes we're going to be looking at examples where it doesn't seem like the order would really matter to anyone. So for example, if you made a playlist of songs and you rearrange some of them, does that matter to you? Maybe not. But does that change the arrangement? Does that change the playlist? And it does. And so anytime we're dealing with the arrangement of things, whether it's important to you or not, if we change the arrangement, then we'd be using permutations. All right. So let's figure out how many top 3 finishes are possible. So we've got 8 people running a race. We want to know about the top 3 finishes. So there's 3 podium places. All 8 people are starting the race. So we assume all 8 people could win. So there are 8 different choices for first place. Not that someone is actually choosing that, but there are 8 different people who could come in first place. All right, once the first place person crosses the finish line, then we have 7 different people who get second place. So the first place person can't keep running around the track and get second place as well. Once the first place person has finished, they're done. And so that's why it's are different objects. All right, so then once the first 2 finishers cross the finish line, then there are 6 people left who could get third place. And then that's it. We only care about the top 3 finishes. So we have 8 times 7 times 6 by the multiplication principle. And that gives us 336 different outcomes for the top 3 finishes. Now, this is pretty easy to do when there are only 3 different outcomes we're looking at. First place, second place, third place. If we were looking at the Boston Marathon, which has 30-some thousand people run it every year, and we wanted to know the top 100 finishes, then that would be, I think it's around 36,000 people run it. So that would be 36,000 times 35,999 times 35,998 times, and so forth and so on. That really wouldn't work very well. So we want a formula to be able to calculate this. Which we don't necessarily need, but it's going to be really convenient for us. So 8 times 7 times 6, we notice that it just goes down by 1 every time. And so that's actually the first part of 8 factorial. So 8 factorial is written as an 8 with an exclamation mark. And that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we want the first 3 numbers there, but we don't want 5 times 4 times 3 times 2 times 1, which is actually 5 factorial. So what we can do here is we can actually just divide out 5 factorial, 5 times 4 times 3 times 2 times 1. Everything there divides to give us 1, the 5s, the 4s, the 3s, the 2s, the 1s. So we're just left with 8 times 7 times 6. Which is 336, which is exactly what we wanted. So this is where we get the formula for permutations. So P in R, where N is the number of objects we have to select from, and then R is the number of those objects we want to arrange. So it is N factorial divided by N minus R factorial. Just like on our previous example, it was 8 factorial divided by 5 factorial, 5 being 3 less than 8. So the denominator, n minus r factorial, those are the arrangements that we just really don't care about. So here we are concerned with the top 3 finishes. What we are not concerned with are the bottom 5 finishes. So basically we're dividing out the number of ways in which we could rearrange those bottom 5 competitors here, because we just don't care what their outcomes are. We are only looking at the top 3 finishers. So that's where this denominator comes from. It's n minus r, meaning r is the number of things we're going to arrange. N minus r is the number of things we really just don't care how they're arranged. So that's why we're dividing them out. And towards the end of this video, we're going to look at another example where we do this, where we take the number of arrangements and then divide out the number of things where the rearrangements don't change anything. So here, the rearrangements of the bottom 5 people don't change the outcome of the top 3. All right, so now that we've looked at permutations, now let's look at combinations. So combinations, that's the number of ways to select r different objects from a group of n objects where order does not matter. So that's the only difference between a combination and a permutation. A permutation, the order does matter. Combination, the order does not matter. So for our example, how many 3-topping pizzas with 3 different toppings are possible if there are 8 pizza toppings that we can choose from? All right. So let's just say, for example, we wanted to order a pepperoni, mushroom, and onion pizza. So P, M, and O, we'll write that as. We could also order a pepperoni, onion, and mushroom pizza. And it's really the same pizza, right? It's got the same 3 toppings. So we can call it the same pizza. We could also order a mushroom, onion, and pepperoni pizza, or a mushroom, pepperoni, and onion pizza, or an onion, pepperoni, and mushroom pizza, or an onion, mushroom, and pepperoni pizza. So all of those are really the same pizza. There's 6 different ways in which we can list those ingredients, but that doesn't make it a different pizza. So with permutations, we multiplied 8 times 7 times 6, which we wrote as 8 factorial divided by 5 factorial, which was 8 times 7 times 6, and that was 336. So we could do the same thing here. There are 8 pizza toppings. So we have 8 different choices for the first pizza topping, 7 different choices for the second pizza topping, because it does say with 3 different toppings, and then 6 different topping choices for the third topping. So 8 times 7 times 6 gives us 336. But within that 336, for every 6 options, it's really just one pizza, just like our mushroom, pepperoni, and onion pizza. So a pizza with pepperoni, onion, and mushroom is listed 6 times within this 336. Now, we don't really want that because that's not 6 different pizzas. That's one pizza that we can read in 6 different ways. So the way that we're going to deal with this is basically the exact same way that we dealt with dividing out those 5 competitors in the race that we didn't really care about the order of. Here, we're going to divide out the number of ways in which we can rearrange those 3 ingredients because we really don't care how we rearrange those 3 topping choices. So we're going to divide by 3 factorial because that's the number of ways in which we can rearrange the 3 toppings. So 3 factorial is 6. That's 3 times 2 times 1. So 3 times 2 is 6, times 1 is 6. And 336 divided by 3 factorial, that's 56. So our combination formula is very similar. So combination in R is n factorial divided by n minus r factorial. So that part is the exact same as the permutation formula. But then we also have to divide out the number of ways in which we could rearrange the objects that we're selecting. And the number of objects that we're selecting is r. So we'd also divide out an r factorial to say we really don't care how those 3, in this case, 3 pizza toppings, we don't care how those are arranged. We just want to know the number of different selections of those 3 toppings, regardless of what order they're chosen in. So that is our combination formula. Now, we can calculate combinations and permutations and factorials using our calculator. So, let's see. Let's move that up a little bit. There we go. So to do this, it does depend on what version of the calculator you have. So what we're going to do with this version of the calculator is we're going to hit Math, and then over to Probability, and then we're going to select Combination, so NCR. In PR is Permutation, so it works the exact same way. For this one, we're selecting Combination. So with this calculator, you select that first, NCR. So the calculator I'm using here is the TI-84 Plus C Silver Edition. The newest versions of the calculators work like this, where you just fill in these blanks. So for us, that's going to be 8. And then I'll use the arrow to get over, and then 3. For those of you with older calculators, what you're going to do is you're going to press the 8 first, then you're going to press math and go select combination, and then press enter, and then you'll enter the 3. So it's a different order. So again, older calculator, you first type in your n before you select combination or permutation, then you select the function, then your second number. So 8C3, and that's 56, which is what we got. We could also do the permutation one, so math over to probability down to P for permutation, so 8 and, whoops, hit the wrong button, 8 and 3, there we go, and 336, which is the answer we got for that one as well. So you can certainly use these functions, and I would recommend that you do, but it is a good idea to be able to understand the formula as well. All right. Now, let's look at a couple of important notes. So these important notes are that N and R must refer to the same type of object. And I'll explain what that means here in just a minute, but it's really, really important. So I would recommend writing this down. So pause the video, write these two things down, because they are two of the most missed things in this unit. And this unit is tough, this section, Combinations and Permutations. It's really tough, and these can be kind of confusing. If you can try to remember to think about what N and R are, and that they refer to the same type of object, that's going to be really key to doing well at this. The second thing is we need a combination or permutation, depending on the problem, for each type of object selected. Now, the type of object, identifying the type of object is a challenge. So that's something we're going to talk about. But these are two important notes that I admit probably do not make sense right now, but we will try to make sense of them. And we'll do that with an example. All right, so we have 5 cards are drawn from a deck. How many hands contain 2 clubs and 2 spades? All right, so let's think here. So one, in mathematics, when this says contains 2 clubs and 2 spades, it does not mean contains at least 2 clubs or at least 2 spades. When it says 2 clubs, it means 2 clubs, not more, not less, exactly 2. So we want exactly 2 clubs, exactly 2 spades. So the first thing we want to think about here is how many different types of objects we have. So let's talk about types of objects really quick. So when we're dealing with different objects, and objects could be anything. We'll look at cards. Those are going to be some easy things because there are multiple characteristics of cards. That's why we use it. We'll use marbles, different colored marbles. We'll use books. We'll use people. Just anything that we can distinguish between. So cards, we can distinguish in a number of ways, and you'll see different examples like this. Cards can be distinguished by color. So color could be an object type. Suit, that could be an object type, which is our object type in this example. That's how we're distinguishing things. 2 clubs, 2 spades. Those 2 clubs could be the king and the ace, or it could be the 2 and the 3. It doesn't matter. It just says 2 clubs. So here we are not distinguishing based on the card itself, which that's called the rank of the card. So Jack is the rank of a card. 7 is the rank of a card. So we can distinguish based on those as well. There's some examples in the homework where we distinguish people by whether or not they're teachers or students, or whether or not they are juniors or seniors. So we are always able to distinguish things by some characteristic. Marbles, like I said, we'll distinguish them frequently by color. So we can distinguish that these marbles are blue and these marbles are red. So anyway, so those are our object types. It is how we are distinguishing from the different types of things in the group. So in this case, we're looking at suits, and there are 4 of them: clubs, spades, hearts, diamonds. And there are 13 cards within each of those suits. But the first thing we want to think about is how many different object types are going to be in our card hand. So we want 5 cards with exactly 2 clubs and exactly 2 spades. So what this doesn't say, but that we have to assume, is that if there are 2 clubs, exactly 2 clubs, and exactly 2 spades, then the 5th card has to be something different. It has to be not a club, not a spade, something else. So really, we're going to have 3 different object types in this card hand. Exactly 2 clubs, exactly 2 spades, and 1 card that is neither of those things. So that 1 card could be a heart or it could be a diamond, but it's not going to be a club or a spade. So we have 3 different object types. So I'm going to draw 3 blanks. Now we can't do this like we did the zip code problem. I very frequently see people try to do that. And the reason why we can't is for this reason. So let's try to do it that way. So draw 5 blanks. So we want 2 clubs. Well, there are 13 clubs, so we'd have 13 choices for the first one, and then 12 choices for the second one, because we've used one of those clubs. 2 spades, so we have 13 choices for the first one of those, and then 12 for the second. And then our last card can be anything that's left that's not a club or a spade, and there's 26 of those. And then we can multiply those together. The reason why this doesn't work, now this does calculate something, just not what we're looking for. This says, here's the first club. That has to be drawn first. Here's the second club. It has to be drawn second. And then here's the first spade. That has to be drawn third. Here's the second spade. That has to be drawn fourth. And then the other, we'll just call it an other, O for other. The first other card, that has to be drawn fifth. So the way we have this written out is that is the order in which things have to be drawn. But that's not the way this problem reads. We just want a 5-card hand with 2 clubs and 2 spades. We could have 2 clubs followed by 2 spades followed by the other card. Or we could have a club and then the other card and then the other club and then both spades. Or a club and then a spade and then a club and then a spade and then the other card. Or any combination that gives us those things. We do not care about order here. So we cannot do it this way. So don't try to do card problems like that. It is just not going to work. So as I mentioned, order does not matter here. When we have a 5-card hand, if we're looking for 2 clubs and 2 spades, it doesn't matter whether those are our first cards or our last cards or however they're arranged. It doesn't matter. So instead, I've drawn 3 blanks because of our 3 different types of objects. So 1, we're going to have clubs. Secondly, we're going to have spades. And then the third one, we'll just call that other. But we know that other category is hearts and diamonds. So it can be any of those. All right. So let's look at our club combination first. So again, it's a combination because we don't care about order. So remember from our hint, so combination is again C-N-R, where N is the number of objects we have to choose from. R is the number of objects we want to choose. So N and R must refer to the same type of object. So what I will frequently see people do here is they'll write 52, 2. There's 52 cards, and I want 2 of them to be clubs. So let's think about that for a second. There are 52 cards. So that 52, that refers to number of cards. The 2, we're saying that refers to the number of clubs. So are those the same thing? Do they refer to the same type of thing? And the answer is no. One of those refers to the number of cards. One of those refers to the number of clubs. And we can't do that. That's not how combinations works. So if we write 52-2, that is the number of ways to choose 2 cards, any 2 cards, from a deck of 52. We can't say they're clubs. We can't say they're aces. We can't say they're red or black. If 52 is our first number, then the second number refers to any generic card. All right. So how do we fix this? Well, we do want it to be number of clubs. We want both of them to refer to the number of clubs. So the first number should refer to how many of them there are, and that is 13. There are 13 clubs. The second number is how many of them do we want, and we want 2 of them. So combination 13, 2. So now both of those numbers refer to the number of clubs. There are 13 clubs. We want 2 clubs. All right, we'll do the same thing for spades. So our combination here again is first number is how many spades are there? 13. Second number is how many spades do we want? 2. So again, both of those numbers refer to number of spades. There are 13 spades. We want 2 spades. All right, the other cards. We'll have a combination for them as well. How many other cards are there? Well, the other cards is comprised of hearts and diamonds. So 13 of each, 26 total. So there are 26 other cards, and we want 1 of them. So we want that other card because we have to account for all 5. Now, this is something else that you're going to notice as kind of a reoccurring theme in this section. You'll often be told that we want specifics for some of the things we're selecting, and then we don't care about the others. So, for example, if we wanted a 5-card hand with all aces, we don't just have to deal with the number of ways to get those 4 aces. We also have to consider the number of ways to get that 5th card. So however many things we have to select, we should always be selecting that many. So here, 5 cards are to be selected. We're selecting 2 that are clubs, 2 that are spades, and 1 that is another. That's 5 cards. So we have accounted for all 5. If we were selecting 6 cards, we would need to account for all 6. So this is really important. Really, really important. And so anyway, just be careful when you're working these problems that we always make sure to select the number of things we want to select. All right, multiplication principle would say that this number of clubs, the number of ways to select these clubs, which, let's see, 13, 2. Well, let's calculate it. So math over to probability, down to combination. So 13, 2. So that's 78. So there are 78 ways to choose 2 clubs, which also means there's 78 ways to choose 2 spades because they're both combination 13, 2. And then 26, 1 is 26. Because if we want to select one object from 26, obviously there are 26 ways to do that. All right, so our multiplication principle would say if there's 78 ways to do event A and 78 ways to do event B and 26 ways to do event C, then we would multiply those together, and that's going to give us 158,184 different card hands, 5-card hands, which contain exactly 2 clubs and exactly 2 spades and 1 other card. So again, even though that and 1 other card isn't listed as one of our requirements, we know that it has to be. All right, let's look at another example. All right, in this example, we have in an election with 6 candidates for one office and 3 candidates for another, how many ballots are possible? All right, so let's draw out a ballot. So we have the first office. We'll call it Office A. And there are 6 candidates. 1, 2, 3, 4, 5. Pretend that's 6 names written out. And then we have Office B with 3 candidates. So 1, 2, 3 names listed there. So what we're being asked here is how many different ways can we rearrange this ballot? And basically, yeah, how many ways can we rearrange this ballot? Now, the order of the names on the ballot, is that important? Well, one, it is important because studies have shown people are more likely to select something at the top of a list versus the bottom of the list. So good or bad, that's something people do. So order probably matters. So if you're running for an office, you probably want your name on top. Because of this, sometimes names are listed in alphabetical order in an election, but frequently they're randomly selected. So for like Fayetteville City Council, for example, candidates actually go in and they draw their name out of a hat or draw a number out of a hat, and that tells them what place on the ballot they are. So they want to try to be fair. But anyway, even if that wasn't important to anyone, rearranging the names would be a different ballot. And so, again, with rearrangement, it doesn't necessarily have to matter to anyone. It just needs to change the outcome. So if we rearrange the names on this ballot, it's going to be a different ballot. So in this case, we're going to be using permutations. All right, so our permutations. So we have two different offices, so I'm going to draw two blanks. So we have Office A and Office B. So that is the number of arrangements of both. So for Office A, we have a permutation. The first number is how many names do we have to choose from? And that's 6. There are 6 people running for the office. The second number is how many names we want to arrange. Now, notice we're not voting here, so we're not going to select one name. In fact, if we put any number less than 6, that means we're leaving someone who's running for an office off the ballot, which is a bad idea in our sort of government system. We don't want to just leave someone's name off the ballot. Everyone who's running for the office should get put on the ballot. So that is 6. So we have 6 names. We want to arrange all 6 of them on the ballot. All right, Office B is going to be similar. So there are 3 people running, and we want to rearrange all 3 names on the ballot. So permutation 3-3. All right, here's where it gets a little tricky. So if we multiply those two things together, we're going to get 4,320. However, I chose that the first 6-person, the office with 6 candidates went first, and the office with 3 candidates went second. But I chose that. That does not have to be the case. We could have a ballot where Office B with the 3 candidates is listed first, and Office A with the 6 candidates is listed second. So we have to account for both of those things. Now, one way of doing that is actually just multiplying our final answer by 2, but I would recommend doing something different, because if it's not 2, we don't multiply by 2. If there were 3 offices, we would get our final answer, because so the reason we would multiply by 2, there are 4,320 ways to arrange the ballot with A first and B second, and likewise there are 4,320 ways to rearrange the ballot where B is first and A is second. So you could see where just doubling the 4,320 would give you the correct answer, and it does. But with 3 different offices, we wouldn't multiply by 3. We would actually multiply by 6, because the number of ways to rearrange 2 objects is 2 factorial, which is 2. The number of ways to rearrange 3 objects is not 3, it is 3 factorial, which is 6. So here's how I would recommend doing this one. So here, so we wanted to know the number of ways to rearrange the candidates for A. We wanted to know the number of ways to rearrange the candidates for Office B. We also want to know how to rearrange the offices themselves on the ballot. So we'll have another permutation for that. So there are 2 different offices, and we want to arrange both of them. So permutation 2-2, which is 2. And so then we would multiply all of these together, and we would get our answer, which is 8,640, which again is double 4,320. But it's important to think about that. So there's a couple other examples like this that you're going to see. So if you ever end up with half the correct answer, it's a pretty good chance that something like this is going on. But again, if there are 3 offices or 4 offices or 5 offices, we don't just multiply by 3 or 4 or 5. We would multiply by that number factorial, or permutation. So I've been saying factorial. Permutation 2, is the exact same mathematically as 2 factorial. Permutation 6 is the exact same thing as 6 factorial, and permutation 3 is the exact same thing as 3 factorial. So just so you know. All of those are just the number of ways to arrange things. So permutation 6 is the number of ways to arrange 6 objects. 6 factorial, also the number of ways to arrange 6 objects. All right, that's it for today. I'll see you next time.